Okay, so I just want to look at a couple more examples for this section. And this is actually example 5 from your textbook. So we want to set up an integral for the volume of the solid region D bounded above by the paraboloid z equals 1 minus x squared minus y squared, and below by the plane z equals 1 minus y. Okay, so let's take a look at what that looks like in GeoGebra. Okay, so I need z equals 1 minus x squared minus y squared. This is not 3D, is it? Let's try again. There we go. 1 minus x squared minus y squared. So there's my paraboloid, and the plane was z equals 1 minus y. Okay, so let's spin this around a little bit, and you can see this region. See if I can zoom in. Oops. There we go. You see the red on top and the blue sort of cutting it out. So we're trying to find the volume of that region. And so what I need to know first of all is what that intersection is, okay? And I said area, didn't I? Volume of that region. Okay, so step 1 is to find the intersection. Of the two surfaces. Well, the two surfaces intersect when their z values are the same. So let's just set them equal. So 1 minus x squared minus y squared equals 1 minus y. And so, let's see, I'm going to get x squared let's do this. Y minus y squared equals x squared. And I could move these over. So I get x squared minus, plus, sorry, y squared minus y equals 0. And I'm going to complete the square in y. Okay, so remember when you complete the square, you add half squared of your b, so negative 1 over 2 squared, and I need to add it on both sides. And so this factors as x squared plus y minus a half, quantity squared equals 1/4. All right, so what is this? It's a circle with radius 1/2 and center 0, 1/2. So let's say here's 1, here's a half, this circle here. Okay, so this is my region of integration. Let's integrate using a horizontally simple region. Okay, so I want to think about how y changes as I take horizontal slices. Well, y goes from the left half of the circle to the right half of the circle. So on the left, this is x equals negative square root of y minus y squared. Now, You may not see that immediately from this equation, but you can see it here from the equation on the top. All right, and over here on the right, I have x equals the positive square root of y minus y squared. Okay, so what are my bounds on y? Y goes, on x, sorry. X goes from negative square root of y minus y squared to positive square root of y minus y squared. And what about y? Well, as I take those horizontal slices, y ranges from 0 to 1. All right, now the volume that we want is going to be the volume under the paraboloid minus the volume under the plane. Okay, so I'm going to set up two separate integrals for each of those volumes, and then we'll subtract them. So under the parabola, I'm going to have a double integral, or an iterated integral in this case, of the parabola. So 1 minus x squared minus y squared. And we said x goes from negative square root of y minus y squared to positive square root of y minus y squared. So that's dy. And x is going to run from, I did it backwards, sorry. dx, everybody with me? We're looking at x. And y is going to run from 0 to 1. Okay, so that's the volume under the paraboloid. And now I want to subtract the volume under the plane. And we're integrating over the same region. So my bounds on my integrals are the same. And I'm going dx dy, but now I'm integrating over the equation of the plane, so 1 minus y. All right, now I'm just going to tell you what that works out to be. You'll get pi over 32. You should pause the video and try that on your own just to make sure that you're confident you can evaluate these iterated integrals. All right, so those are the kinds of questions or problems that you'll see in this section. We have one last topic, and that's the average value. If you remember from Calc 1, we used the integral to find the average value of a curve in a certain interval. And we can do the same sort of idea for a multivariable function. So if f is integrable over a plane region R, then the average value of f over R is 1 over a times the double integral over R of f of x y dA, where A is the area of R. Okay, so I just want to do one quick example of this. So let's find the average value of f of xy equals x over R, which is the rectangle with vertices 0, 0, 4, 0, 4, 2, and 0, 2. Okay, so I have 0, 0, 4, 0, 4, 2, and 0, 2. So here's my rectangle. Well, my formula says the average value is 1 over the area of that rectangle times the double integral over r of f of xy dA. Well, this rectangle, has side lengths 2 and 4, so its area is 8. So I have 1 over 8. When I integrate over a rectangle, I can use my region as vertically simple or horizontally simple. Let's go this way. Here's my delta y. So x is going to run from 0 to 4. F of xy is x, and that's dx. And then y is going to run from 0 to 2 dy. All right, now we've done several of these, and hopefully you've tried even more in WebAssign, and so I'm going to assume that you can do this one without too much trouble. If you get stuck, let me know. But what you should get here is 2. So the average value of that function over this rectangle is 2. And that makes sense, right? So this is f of xy equals x. And if you think about this rectangle, here's 2, right? So on this half, f of xy is between 0 and 2, and on this half, f of xy is between 2 and 4, right? And so it makes sense that the average would be right here in the middle. All right, go ahead and try the homework, and again, let me know if you have questions.